Okay, so as I was setting up, this is a hackathon organized by the ESS Cyberinfrastructure Working Group on Model Data Integration. The last information from the previous hackathon that was held 2 weeks ago on ELM is available at these links. And we're gonna just launch right in here and get started. And talk a little bit about ILAM and about benchmarking before we launch off and start doing things. We're let's see what's in the chat. Okay, links. Okay, thanks. So you know, ILAM is a software package. It's a bunch of things, and I'll tell you a little bit more about it. But it was designed for a particular purpose, and we're sort of extending the scope of ILAM to help us do things like evaluate watershed simulations. So for ILAM, we think of a benchmark as a quantitative test of a model function that we achieve through comparison with observational data. And of course, as you would expect, you know, acceptable performance on a single benchmark is necessary, but not a sufficient condition for a fully functioning model, right? We need lots and lots of these kinds of metrics for evaluating models. A very nice thing about ILAM is that it has this concept of a functional relationship benchmark or variable to variable comparison. And this allows us to test model responses to forcings and see if we're getting the right sort of response of either the Earth system or something over time. So an example is the figure on the lower right, where we've plotted net primary production versus precipitation. The observations are the solid round balls there. And you can see that from the two models that we're comparing, they do a pretty good job at low precipitation values of having somewhere in the neighborhood of the right NPP and the right relationship of NPP to precipitation, but at very high precipitation in the observations, NPP sort of rolls over and starts to decline, but the models don't do that. So this is an indication where the models are not giving the same kind of result that we see in the observation. So this is a clue that we may need to go work on the model. And as I already mentioned, you need lots of benchmarks, right? Drawing on a broad set of independent observations to really evaluate model performance. And we want to usually do that at multiple scales. So we're going to talk about ILAM today. And ILAM, as I mentioned, is a bunch of things. It's a community organized activity, a coordination activity. It's also a software package that we're going to talk about today. ILAM may also be used to describe the philosophy with which we, use to develop and implement that ILAM package. And you might just talk about ILAM as the set of supporting observational data sets, which are useful in various other contexts. But all of that is sort of gathered in this one concept of ILAM. But the original activity as an international activity was put together to develop accepted benchmarks for Earth system models and promote the use of the benchmarks for model intercomparison. Also to help us strengthen the linkages between the experimental remote sensing and Earth system modeling communities and build out open source benchmarking tools like what we now call the ILAM package. The package itself generates lots of diagnostics, both in the form of tables and various kinds of contour plots. At the highest level, it produces a portrait plot, and I'll show you an example of that in a moment. But we typically evaluate model results by comparing them with observations, and we look at the bias, the root mean squared error, the phase shift or seasonal cycle, and the interannual coefficient of variation, and some kind of spatial distribution score, like a correlation, spatial correlation. And the overall score that a model is given is the average of all of these metrics, where RMSE is double weighted. The graphical diagnostics again consist of spatial contour maps, time series line plots, Taylor diagrams, and you'll see all of this very soon. But we also generate these same kinds of tables and graphical diagnostics for those functional relationships that I mentioned in the previous slide. This is just sort of a laundry list that may even be a little out of date of the various data sets that we have in ILAMB when we're doing mostly global model evaluation. And what you're going to do today, G2 is going to talk a little bit more about, and that's the extension of all of these capabilities for looking at runoff and doing watershed evaluations. But some of these data sets still apply at that smaller scale. But you can see that, in many cases for a given variable, we may have multiple data sets, and we have the ability to weight these by how much we think the model should, how much we think they correspond to the spatial scales and temporal scales of the model themselves. And just a real quick example here. This is an evaluation of CMIP5 Earth system models versus CMIP6 Earth system models. There's a one-to-one correspondence. So these all had to be models that participated both in CMIP5 and CMIP6 and had prognostic productivity, plant productivity in their CMIP5 and CMIP6 models. And what we see from this is we can look at those scores that are included in the little boxes there. The A part, the upper part of that figure is a subset of the land model evaluation, and the bottom part is a subset of an ocean benchmarking evaluation that actually comes from the same software base. But what you see is, for the most part, the CMIP5 models had relatively worse scores than the CMIP6 models. So this indicates that the models improved between those two generations. And so ILAMB is very useful for doing this kind of multi-model evaluation and comparison, or for evaluating multiple versions of models as you're doing development along the way. And there's a lot more packed into here that's not needed for today's activity, but this gives you an idea of one of the common applications for which we originally designed ILAMB. And I think that's it for me, and we're going to switch over now. And I think this is where G2 is going to talk, right? Or
Nate.
We switch to Nate first. Right. Okay.
Can you let me share?
Let me stop sharing. It's all yours, Nate.
Okay. Right. And so just to continue on where Forrest left off, we wanted to just step through what it is that ILAMB actually produces. So you may have seen those portrait plots. Those are the things that get kind of pasted onto presentations, and it's what a lot of people kind of look at, but ILAMB was not really intended to kind of stop at that portrait image, but allow you to really drill down and understand and try to explain why you have these differences. And so these are all live results on ilamb.org. If you go to ilamb.org and click on the results section, you'll see a number of studies that we cached there, and I'm just showing you details from the CMIP5 versus 6 comparison, with apologies to those of you who have been forced through this many times. But if you expand on any one of these particular variables, you see on the y-axis are all the different variables that we measure performance with respect to out of the models, and across the x-axis here are all the different models that we have. But you can click on them, and what it exposes is the list of underlying data sets that contribute to our synthesis of how well a model is performing in that given variable. And when you click on the particular data set, a new page opens up that has a huge table of data, of information, and as well as all the kind of components that make up the overall score, which you're seeing on the front page, with some coloring here to give you an idea if you're better or worse than the mean model in that particular component score. And so when you click on a particular model and keep scrolling down, you'll get that model's mean value and bias maps and everything all pull up like this. So you can really dig down and try to understand why you're seeing a particular performance. So we have all sorts of maps, and you can customize this and put whatever you want. We look at the spatial distribution of the mean information, and we can also then look at the integrated regional means. I say regional means because one of the options up here is that, you know, you can compute ILAM for particular regions. Like if you wanted to look just at the Amazon, then you can do that, and all the numbers now have changed to be reflective of that region, as well as all of the plots. And so this allows you to kind of drill down and understand what's different about your model, and what might be causing a change in score. Looks like, oh yeah. And then we also do relationships. And so like Forrest was saying, and sometimes you need to use the zoom on the browser to get the plots to all render nicely. But you can come in and then look at how a mean relationship with, say, GPP to precipitation looks like from observational data. And you can compare that to the same distribution that you get out of the model in a distribution sense. But we also look at the mean functions, because if you just look at it from a distribution, you'll see some cells down. Essentially, if you had a precipitation bias in your model, then this distribution is going to be shifted, but it has nothing to do with the relationship of GPP to precip. And so we also look at the functional relationships as well. And so in short, this is what it is that we want to do, but we want to start to put something together that looks like this, but that could be applied for watersheds. And a lot of people have the perception maybe that ILAM is just for this global model output for monthly mean data, and that is where a lot of our work has been. But the software itself can support lots of different kinds of comparisons, and we hope to illustrate that today with an example in this tutorial. Now I'll pass it back to G2.
I'll share a couple of slides to just orient us to some of the things that we'll talk about in the tutorial today, and on watershed specific analysis and capabilities that we have in ILAM, and give you a little overview about the case study that we'll be working on for the hands-on part of the tutorial today. And then some high-level information. So let me share my screen. All right, I hope you can see this. So Nate talked about global scale, model benchmarking work that that ILAM has been used for and was primarily developed for a long period of time, and we have done in last a year or two, supported by various different projects. We've built new capabilities in ILAM for evaluation of watershed scale models as well. In contrast from the global scale model, watershed scale models are actually running at a higher resolution. So we also want to be able to look into high resolution data sets and bring those in. We also want to be able to tap into point observations, such as from USGS gauge stations, for flux towers and so on, if we are looking at biochemical variable. And we'll talk about, we'll go through some of the examples today as to how do we integrate those data sets within ILAM. Since we will be primarily kind of focusing on hydrological processes, I wanted to make a note that we may have a combination of routed versus unrouted models that we work with. For example, ELM type models that we have, and land surface models that are not really doing a full flow routing, but models like ATS that's doing it's a fully physics-based model at high resolution and is doing complete routing. And we have built capabilities to be able to bring all those models together. Now, it's important to note that the aggregations, the way we look at those discharge, are slightly different. So, for example, for unrouted models, we actually look at the contributing basin and aggregate the gridded flows that we may have available. But for the routed models, they are able to just simply output the hydrograph or the time series at the relevant gauge locations that we can bring in our analysis. And within ILAMB, we've built several model-specific readers to read the native model outputs. And what that means is that these at the bottom, I just listed a couple of models that we have already started to work with. So ATS, SWOT, and national water models. So some of these models that we think that the community is using, we're starting to develop the routines within ILAMB. So you don't really have to make any do any pre-processing, post-processing on your model simulation, and ILAMB will be just directly be able to read the simulations simulation outputs from models like ATS. And again, we'll go through some of those examples in the next set. So for today, this is just to orient. This is an area in Washington State. This is where the PNNL SSFA is working, and some of these model simulations were actually done by PNNL group, and Xingyuan was able to provide some of the data sets that we will be actually using in our evaluation today. So I've just overlaid on the satellite image are these HUC-12 watersheds. If we look at the DEM, which and I have a link for the data sources here. So this is what the digital elevation map for the region is going to look like. This is a HUC-10 basin where model simulations were conducted by the PNNL group, and these simulations were conducted both using ELM, and this was the exact watershed that if you were part of the ELM hackathon 2 weeks ago, this is the watershed that you were simulating. So we are going to use those simulation outputs that you have created last time, and we're going to stage all that data for you to download if you don't have it handy or if you didn't attend the last session. But we're trying to use the same watershed and do the evaluation. Then, and the same watershed was also simulated using ATS, SWOT, and national water model. So now we have 3 routed models and 1 unrouted model exactly for the same basin that we want to be able to bring it all together with an ILAMB framework for a set of benchmarking and evaluation. So if we look at within this basin, there's one USGS gauge station present, and there's a list of, and that's the blue dot on the map right up here. It shows the location of the gauge station. And if we go to the USGS sites and look for the contributing area or the upstream basin that they think is contributing to this particular gauge station, this is what the basin is going to look like. So there's a slight mismatch between what the observations are looking at versus what we are simulating, but routed models are going to be able to still get us very close to the same contributing area. But something that we'll come back to afterwards later on, after we've gone through the hands-on exercise, that why these are important. So for evaluation data sets, we'll get discharge data from USGS gauge stations, and USGS provides nice REST APIs, and we have completely automated this process, so you never have to download anything. ILAMB will do all that for you, water vectors and so on, all the basins. Anything we can get from NHD, we have fully automated that process. For evaluation of biogeochemical variables like GPP, LAI, evapotranspiration, we are going to be using 500-meter resolution data from NASA MODIS. Again, we have developed scripts to automate this download for the watersheds, and we'll link once we summarize this hackathon. We'll send a link to all those repositories and code that you can just simply use. Where you can just pass on a shapefile or a JSON for your AOI and automate get all the data sets that you need. That code will also do any transformations, any modifications to the NetCDF files needed, so that ILAMB can work with it. So all those pieces are automated. Of course, that you will have to have a NASA Earth Data account for this. Again, depending on size of your watershed, it can take few minutes, 5 minutes to 10 minutes to actually get this request through. So we are not going to go through that step. So I just want to make a note of this and then give you the code later on. And we have already put together the data set that will ask you to download for today. And then there's a lot of metrics that you saw in CMIP 5 versus CMIP 6 example that Nate showed you. So we are inheriting all those benchmarking metrics that are supported by ILAMB within the watershed context as well. And then and we implemented metrics like National Cliff Efficiency, Klim-Gupta efficiency. So these metrics that are often used by hydrological community. We're starting to build metrics and plots to assess low flows versus high flows and the timing and the magnitude of it. Again, there are a set of metrics that we have already built, and we would like to get your feedback as to what are the additional metrics that we should start to implement within ILAMB. So this kind of sets up the stage for the example problem that we will work with. So I'm going to stop here, and then we'll get into a hands-on tutorial section of today's session, and I'll pass it on to Nate.
Thanks, Jitu.
And if you have any questions, you can feel free to unmute yourself and ask away, or put it in the chat here, or Slack, anywhere.
Okay. So the big question then is how do you go about then doing all of this? And I have some instructions. I just posted a link in the chat, and I'm going to go ahead and go through the installation because it shouldn't take that long. Just to show you like how it works. So I'm just starting here in a blank directory that I have, and we're going to be using Anaconda. There are other ways that you can install this software, but a couple of ILAMB dependencies depend on C libraries like MPI. It's how we achieve multi-node parallelism, and the UD units library. And so if you are to use pip to install, you're not going to get those dependencies. But if you already have them built on your system, then pip will just install on top of that, and it's fine. So if you're comfortable installing the software yourself, then by all means go ahead and do that. But what I'm just going to sit here with the instructions here on the right-hand side and show you how this goes. So what we're going to do is use Conda, which I've already installed, and create this blank environment. I recommend that you put all of this in a separate environment because then Conda will be able to install without as many checks on all the other packages that you may have in that environment.
And if you have Conda on your system, please follow along, and it should not really take a huge amount of time.
Yeah, that's the hope. It shouldn't. Of course, things always break, right? So if you're not familiar, you create an environment, and then you activate that environment, and this environment has nothing in it. No Python packages are yet installed. If you're new to Anaconda, there's a channel called Conda Forge, and you need to make sure that your Conda is picking up this channel. This is where a lot of people have put their own kinds of packages to be supported, and ILAMB is a package available in that Conda Forge channel. So it's going to warn me to tell me that it's already in there. It doesn't hurt to add the channel again. It will detect that. And once you're there, then you just need to say Conda install ILAMB. And it's going to go through, and this will take maybe a few seconds, and it's going to go grab the build for your particular architecture and put it in. Now, we did have some experience with some of the newer OS architectures, build not being available yet in Conda. And if that's the case, you'll have to revert back to pip, and we may have to talk about that offline, but it should be there. And so it's going down and pulling all the metadata and the packages that are required in order to run ILAMB. And hopefully it'll just take a few seconds. And while that's going, of course, if you have any question or comment, please feel free to insert it here. No, so it's going to prompt me do I want to proceed by grabbing and downloading all of these packages. And what you're really installing is the last kind of release version of ILAM that we had, but it's a convenient way to get kind of all of our dependencies installed in a fast way, simply because it's already packaged sitting up there. I feel like I should have music on or something. Okay, so that puts that in there. And if you keep reading my documentation, I'll tell you that what we're showing you today is it hasn't been released yet. A lot of it was developed specifically for this. And so I'm just going to recommend that you clone our repository and then move into that repository. And then we're going to install using pip on top of what we just installed. And so also, you'll notice there's also this dot square bracket watershed. This is a way in Python that you can install extras. So that all the additional packages that we need to do this work on watersheds, I put in kind of extras so my regular users don't need to have them all downloaded. So this is just going through and putting on top of that those extras. If you actually got our email and tried installing this yesterday, you may have gotten an error which crept up because yesterday NumPy released 1.24.3, which actually breaks ILAM in a catastrophic way. And so we have to figure out what that is. And so anyway, it should downgrade you and install to 1.24.2. Now, in the documentation here, I also recommend that you go ahead and install wget. If you don't have wget, I mean, you can just type wget and see if you have it. Also, you don't actually need this. ILAM is just going to give us some extra warnings, so I'm going to skip this for now, but it's not pertinent to anything that we're using today. And if you got this far, I recommend usually people launch this little Python command, which will import ILAM and then print out the version, and you ought to get some kind of numeric result out. And if you got that far, then you're installed. Is there any question?
So it looks like a couple of people are having this issue with ILAM not found, and that's likely the architecture issue.
Okay, yeah, I can't see chat from here.
Yeah, so the newer, looks like there are some new Macs that are not getting supported, like Conda.
Yeah, I wasn't aware of that until last night, or I would have tried to make sure that it was working there. If you're not able to get ILAM installed, these instructions are still here. We can fix the Conda problem, but that you can view the output little bit by little bit yourself. Are there any problems other than Conda? If you're one of those Mac people who are having problems, if you have the MPI, some version of MPI installed on your laptop already, or if you're using Homebrew to install that already and know what I'm talking about, then you can do that. And you would also need UD Units 2, which I believe is also available in Homebrew. And once you have installed both of those C libraries, then you can just use pip to install ILAM. You would just need to clone the repository and execute this pip command, and it will wrap around the C libraries that it finds. You don't have to do it inside a Conda environment. G2, is there any other question not related to that?
No, I think there aren't really any other questions, just a few people having this issue. So hopefully the PIP method can work for them.
Yeah, and I should have put the link up at the top, but if you go to ilamb.org/doc, there's a bunch of tutorials and there's installation instructions. The installation instructions are a little dated at this point, but there's more information there about how to install, and particularly if you're trying to install like on an institutional cluster, there's some information there. This MPI dependency causes us some difficulty. Okay, then for now, then we'll move on here. Well, from inside this ILAMB directory, it doesn't need to be here. It can be anywhere you want. It's just a convenient place to put it. I'm just going to make a directory called tutorial and go into that directory. And we need a place to put our model results. And so I'm going to create another subdirectory just called models. This is just a convention. You can call it really whatever that you want. I'll explain what is important in just a minute about how you name things and what you put someplace. Now, here in this models directory is where we want to put our ELM output. If you were here 2 weeks ago, ran your own ELM output, then you can run ILAMB just straight on that data. You'll need to get it off of Docker, out of your Docker instance. And I thought I put, oh yeah, I put some recommendations here. You can either move it, and Dan was talking last time about going down and actually clicking download, and or you can spin up ILAMB inside your Docker instance. You can do all this installation. The problem with that is every time you spin up a new Docker image, because this does not exist in the image, you'll have to reinstall everything again. And so I recommend that you try moving things out. But if you weren't here for the tutorial, or maybe your run didn't go, or you don't want to mess with getting your own output, and you trust that I have run the output correctly myself, or G2 did, you can just grab this file here, elm.pgz, and I put it here in the models directory, and I'm just going to extract it. And you'll see, a whole bunch of files. You'll notice that this is exactly, the file designation that you'll find in there as well. I have the H0 and the H1 files embedded in there. Now, if you go digging around those files, you'll notice that they're a lot more sparsely populated than the real ones, because to keep the file size reasonable, I weeded out a lot of files. And so really, it just has a few variables that we're going to use in this, so that the file size kind of remains about, excuse me. So the file size remains something like 100 something megabytes. Okay, so this means we have now our model output from the runs that we did last week. And we also need a place to put down observational data. So in this first example, we're going to use the regular ILAMB software, and all we really need is some observation that's more relevant to the watershed scale simulations that we did. And that's kind of like, I think, the real obstacle to using ILAMB as is in these kind of simulations, is just the resolution of the data that we have is not kind of interest to something as small scale as a watershed. And so I'm going to create a data directory, and inside that, I'm going to create a modus directory. And here in the tutorial text, I give you some information about how to use Appears. G2 mentioned it. I mean, you can go to this Appears website and draw a box or submit a polyline, and it will go and tell you what all data is available. It's a nice way to get this usually really huge data in a nice kind of small bite-sized piece. So we've already done that for you. I mean, it's not instantaneous. You'll make a submission to the NASA Appears website, and it will take it, maybe a half an hour to process, depending on how busy they are and how much data you want. And then it will provide you a link that you go down and download it later. And we had to do a little bit of cleaning up as well. And that those scripts are being populated here in this ILAMB Watershed's GitHub area. But what you can do is simply go and grab the data off of our website again. And so you see here, we have this American River watershed data. And this just came right off of the Appears website. And it's at appropriate, let's do NC view. It's at a resolution appropriate for those particular watersheds. So you can see here, this is, did you say HUC 10, G2? HUC 10 or the HUC 12 watershed that G2 was showing. And this is the MODIS GPP data that we have for that particular location. So now we have both data and models. And if you look at your directory, they should be organized something like this now. You have your top level directory, and inside you have data, MODIS, and the American River Washington, and then the models, ELM, and inside, you have all your H0 and H1 files. Is there any question up until this point? And G2, please pass the questions on to me, because that's one thing Zoom should fix, I think, is the ability for the presenter to see chat.
Yeah, no, and it looks like Ethan has some suggestions for getting around the conda problem that we have with ILAMB right now.
Oh, thanks, Ethan.
And yeah, and we'll of course look into fixing that issue later on. Okay,
and so so that's it. All this so far is really we're just organizing ourselves. And now we're going to start developing the input files that you need in order for ILAMB to process. And so the first thing, ILAMB is built to read what we call just a configuration file. And so I'm going to open up in my text editor, which I'm using Emacs. If you're a VI person, no judgment. You don't judge me, I don't judge you. And but just use whatever your favorite text editor here is to open up a file in this tutorial directory for watersheds.config. And in there, I'm going to copy and paste this text here, and I'm going to explain what each one of those corresponds to. It's a little small, but anyway. The first two designations really are just organizational. In the past, that in regular ILAMB, this was like the ecosystem variables or the hydrology variables or whatnot. And then the H2 headings, in regular ILAMB were like variable names. And in our case, we're just choosing to organize the information a little differently, as what we want to see is performance averaged over watersheds. And then this top level heading, we're just putting US watersheds. I mean, that's the only ones we're going to have, at least initially. But you could envision kind of separating it out by maybe like East Coast versus West Coast, or maybe some other designation that makes sense to you. But this is just a placeholder for now. I think that the real important part is this tag here. So this is going to be an actual data set. You can insert in between these square brackets any name you want, as long as there are characters that can be directory names. So, nothing that can't be a directory name, because ILAMB will end up building a directory system underneath, and it will cause problems if you don't. And then we're just going to tell it which variable to look for. We try to stick with CMOR variables as much as we can, just to be good citizens and promote standard use, at least coming from the global community. I realize watershed community is different. And then we specify where the source is. Now, remember, I said that it doesn't really matter how you organize your data. That's mostly true. But you'll notice that however you chose to organize your data, it has to be reflected in this file. And so here I've just specified this location. And in a minute, we're going to use an environment variable. This location will be relative to where that environment variable ILAMB root is set. ILAM allows you to control things about how the units look. We were talking with people, because we use UD units, you can really leave your variables as long as they're CF compliant units, things that UD units will recognize. Then ILAM can do all the conversions internally. And then here I'm just specifying a color map as well. This is we found that when looking at GPP, green is pretty intuitive, and so we leave that there. So this is how you set up which data sets you want to compare against. The second thing that we need to, first of all, is there a question about setting up those data, something not clear about setting up those data sets? Everything that I'm saying here is also represented here in this text. So if you feel like you missed something, then you can go back and look at it. And also what I mentioned before is ILAM is set up to look at this environment variable called ILAM root. And this is what makes your configure files portable too, because you can, or as a community, you can build a configure file, right, and a set of observational data that go with it, and then instruct people to download that and have them point ILAM root to the location where that is, where you're working from. And so in this case, I'm just going to use // but this could be an absolute path as well. But this will work as long as you're running kind of from this directory, and otherwise you would need to specify a full path. Okay, so that's half the equation. Half the equation is getting the variables, the data sets set up. The other half is setting up your models. And in this case, we've provided a kind of new way to specify models. Now, ILAM has this problem that we have maybe 3 or 4 different kinds of configure files because it's been around a while, and I just haven't gone back and removed the old versions. And so right now I'm using these YAML, or if you're not familiar, yet another markup language files. And essentially we're going to use this to specify how we want to set up the ELM model. And I've told you here to copy this text in to this file. What this represents is it gives us a place to start the definition. It's just going to build a dictionary that gets imported into ILAM, and whatever is in underneath this heading here is going to be passed into the keywords of the model result constructor. And so you can stick anything that's in a keyword, if you know what I'm talking about, in this YAML file, and it will get passed in. And so the regular kind of way that ILAM functions is to assume that what you have by model is a regular latitude longitude grid model that has been Seymorized. It's actually a little more flexible than that, but it does anticipate that all of your model variables are output on a rectangular grid. And in the case of ELM, the raw output is not, right? Raw output is a 2D array of time and another dimension called land grid, if you haven't ever looked into that. And so it's unstructured in this case. And so what I've done is I've written my own kind of model result, which it knows how to read that output. And so when I specify a type here, that's what I mean. If you were setting up just a regular model you got off ESGF or an E3SM run that's been Seymorized, then you just wouldn't put anything here and use the default that value. The configure allows you to specify a color as well. This is like, if I have a line plot when we're comparing multiple models, you'll see this come out in a minute. This will be the color that ELM is always colored by. And so this helps to kind of keep things consistent. Then I give it a path. I tell it where to look for the model results. In this case, it's relative to right here. You could specify an absolute path. Your model results don't need to be where I put them. They can be anywhere, and you can just tell me where to look. And you can also specify a list of places to go looking. You might have some of the files here and some of the files there. You can rearrange in that way. And then another thing that ILAM does that's very helpful is that it allows you to specify synonyms in a dictionary. And so the big problem, is that inevitably models will call things differently. And it really stinks to feel like you have to pre-process your output, post-process your output just to see to run it through something else, when really it's just a name change. And so we try to be helpful in that way by allowing you to specify synonyms. So in this case, capital GPP, right? What this says is that when you ask for little GPP, return out of E3SM capital GPP. I mean, in this case, it seems kind of trivial, like why not make them case insensitive? But they're not always that trivial, as you'll see in a minute. And so that's how we set up the models. So if you list the directory now, we have our data directory, we have our models directory, and the models YAML file, and the watersheds configure. And now we're ready. When you installed ILAM, part of what you installed are also a set of ILAM commands, and one of those commands is ILAM run. And we're going to specify the config argument and tell it which configure, the watersheds configure. And then we're going to specify what the model setup file is. In this case, it's models.yaml. And we're going to run. And unless I forgot something, should take a few seconds. It's looping through now, processes the configure file, looks to see what it found, processes the models. It should tell you here that you may get some warnings. Notice I didn't install Godal and it's warning me. It's fine. Warnings are okay. Setting up ELM from the models run. It parsed the configure file and it found this modus GPP. This just means that it did in fact find the output. And then let me just reduce the font size a little. Then it ran it. ILAM occurs in two phases. The first phase, it goes ahead and it runs the analysis bit. And that's what compares ELM to this modus GPP output. And it creates some intermediate analysis files. And then it, in a second pass, because you could have multiple models and I need to know the plot limits across all models, in a second pass, then we loop through again, build up what those limits are, and then it renders all the post-processing. So this should only take a few seconds in this case. And if you relist your directory, you'll notice that there is now a build directory here. And this build directory, you can, if you have the tree command, I find it helpful. This build directory just contains a hierarchy of web pages and images. So you'll notice a couple of like log files and index.html, and underneath it, there's a directory structure that's built right out of your configure file. You can make it look exactly like you want. And then underneath all of that, you'll notice a bunch of images. So anything that you're about to see in the web pages we're going to look at, you can dig around here and just find the images already loaded up. And you'll also notice that we store the intermediate netcdf files. So if there's something here that you want the plot, but you don't like how I plot it, or you want it higher resolution for a publication, all the information just sits right in these files, and you can create some higher res plot out of that if you so choose. To view this output, you can just say Google, Chrome, whatever your favorite browser is, and just open up the file directly. The problem is that file uses JavaScript to load a JSON database, and browser security won't let you do that directly. You have to kind of emulate a server. And so in the instructions, even I recommended that you navigate into this build directory and then use Python to emulate a little server. When you do this, you're going to get this little link here, and you can tell it to open that link. And let's put this over here, please. What if I ask nicely? Yeah. And so here you see a website much like the historical one that I showed you, except it's far less impressive. You only have ELM because that's the only model we've been looking at, and we only have this one output, but you got to start somewhere. And so there's only one model, so there is no relative difference. It's all 0. But if you click on this modus GPP, what you get out of this now is the same information you had before. This is using all the regular ILAM analysis, and it's plotting out a lot of the period mean GPP values and a lot of the scores. And you can scroll through and see a lot of the plots. Now, this is a little bit strange. It makes more sense probably in our global context, but after a lot of iteration with the community, when we plot the benchmark and the model means, we plot them over their original grids because a lot of people were confused by why we were trimming away things for them. And so this is the mean modus GPP value, and this is the mean GPP value we got out of our model. There's a couple of oddities about it. I mean, it's a bounding box around the watershed. ILAM is going to take care of that intersection here in a minute. But you'll also notice that there were some hard zeros out of the ELM output, and I'm not totally sure why that is, but if you go and check the time data and look, you'll notice that there are about 123 cells where the GPP is a hard 0. And so that explains these little white areas. But internally, ILAM pulled out that land grid data and created this gridded product, and it would work even if your data wasn't an absolute square. It would actually, if you only ran, let's say, on just those cells in the American River Washington watershed, it would reshape it and insert nans in place where you had no data. So then ILAM computes this intersection. You'll also notice there's this big stripe here. This is because it's picking up one of these zeros and doing a nearest neighbor interpolation, and so it interpolates to 0 all the way out. We need to investigate this further and get some better science results. Some of that, though, is just going to be about being more careful about what we set up. Like any model intercomparison, the protocol of exactly what's run is important. And so, moving forward with this as a group project, then I think we should be more careful about how we set up these runs, and it will make the results much more interpretable. But this is just a demonstration for now. But you get all the same kinds of things you get out of the regular ILAM. The code just works right out of the box, including kind of regional mean annual cycles that are there. So let me pause for just a minute and ask if there is any question or reaction to any of that.
Hi Nate, I had a question for you.
Yes.
Yeah, with the sort of model type for the ESM that you defined, are there different types available from ILAM, or is there a way to kind of define those yourself?
You can build them yourself. So you can build them yourself. I'm going to show an example here in just a minute of another kind that you build. ILAM is in a bit of a transition now. For a long time, I've been working on a rewrite that uses X-array pretty predominantly, that I just can't seem to get enough momentum to get it all moved over. And so if you dig in there right now, you'll see some kind of, there's an old way of doing things and a new way of doing things. And so it might be a little confusing if you looked at source code, but I can walk you through it.
Okay.
Because right now it's kind of doing both.
Makes sense. Thanks.
Okay. Any other question? So really, what I hope that illustrates is that the code base is relevant to watershed scale. We merely need to find, we need to find reference data sets that are of interesting resolution. And hopefully it also suggests that we actually need people to run these models over these watersheds, right? We're limited. ILAM was very nice because we collected all this gridded information, but also we had something like CMIP and ESGF to download a ton of model output, and we could advance it. And so, to do a whole lot more, we need the community to be running these models, to find a place to submit the output to, so that we can do more rigorous comparisons. But that's not a problem that we can solve right this minute. But let's see what else can we add now to our analysis. And this is something that we coded up just for this particular tutorial, and that is using USGS discharge data. And so you may be familiar that USGS provides you an interface to go and grab all the data automatically. And so this is, I would say, kind of a data-less comparison in that I'm not going to add data to my data directory like I normally would. I have written a particular, what we call confrontation, that knows how to go and query that data. And so I'm going to take this text here and open up my watersheds.configure file. And I'm going to insert this, just append it down to the below. I'm leaving it inside the H2 heading because this is still over the American River Washington watershed. Now, you may not know that, but we know that because we went looking for what's called the USGS site code. If you're not familiar with the site codes, you can go and browse on this interactive map. There's a link here to maps.waterdata.usgs.gov. And you can zoom in and look at the watershed that you're interested in studying, and that you will find the sites. And one of the pieces of information you need is the site code. You also need to tell me kind of a date range, rough date range that you want to look at. USGS just doesn't seem to, unless I misunderstood the API, it doesn't want just to give me everything. It wants me to say what I want exactly. And so here we're just going to specify a date range. And you'll also notice here that I'm specifying this variable called C type. This is just like you can create your own custom model type, you can create your own custom, what we call confrontation type. It's just a word that we use to mean the encapsulation of the observational data set and the code, which compares that observational data set to an abstract model object. So the model object is really just responsible for loading something into memory and giving it to the confrontation. The confrontation is responsible then for taking two variables and comparing them and spitting out output. And so all the magic kind of happens inside there. For now, we're just going to tell it we want this comp USGS. There's one other thing that we need to do here back in the models.yaml, because the USGS confrontations are going to ask for discharge. And the variable that we want to use in ELM is actually Q runoff. And so I need to add a synonym. I need to say, hey, if you're asking me for discharge, then actually go grab Q runoff out of ELM. And because we changed the model, we also need to remove this cached entry. If you just list what's inside the top level build directory, one of the files that you get is this elm.pickle. And because especially on systems like OLCF or NERSC, if you're running ILAM there, when you instantiate a model, you are usually looping through a bunch of files. You're hitting the file system a lot, and that tends to be extremely slow. And so what I started doing was, once you've built the model object, I would just cache that in a pickle file. And if the pickle file exists, use the pickle file. And if it doesn't, then build it again. And it sped up, my runs by a considerable amount just by not looping over the file system. And so we've changed something about the model here. So what we need to do is actually remove this pickle file. And I think this is in the instructions too. I'm just a little ahead. Yeah. We just need to remove this pickle file so that it will regenerate and find the synonym that we're looking for. Otherwise, it won't get loaded in there together. And so you can, Control R and go back and just grab your ILAM run command again and just rerun. Now, this time through, the modus confrontation has already run. So again, it will come through. It's going to build the models again, this time from scratch, but with our synonym. It finds the modus GPP watershed, and it also finds this American River near Nile, Washington. This is the name that we typed in. This is a name that got queried off the USGS server automatically. We might work on cleaning that up and making it look a little more parallel with what you see when we handwrite them out. And now it's going through and it's running confrontation with Q runoff from ELM. Now, the way I've written that confrontation is that if you query the model and what you get out is a gridded output, it's going to actually integrate that gridded output. And so this really assumes that the runoff out of ELM is instantaneously transported to the outlet. So you wouldn't imagine that this is terribly good, but you can do it, right? And you can see in some way when you don't have the routing of this runoff model, like what exactly are you missing when you compare to something perhaps that does, which we'll get to in just a second. And so it took a few more seconds here. It actually had to query that data and download it as you went. So you would need an internet connection here. We're talking about ways to just automatically cache it instead. And then it finishes, it makes the post-processing. And this last step here takes a few seconds because again, it's downloading some higher resolution data to make what you'll see in the plots in just a moment. While we wait here for the computer to finish, is there another question?
Nate, I think just to add here, in this particular case, you want to specify which H10 or H1. So the Q runoff that we're using from ELM, these are monthly runoff or these
No. So the confrontation is written to ask for the daily. And so when I build the E3SM model result, I actually have a list of what all variables are available at monthly resolution and daily. And if you didn't have Q runoff in H1, then it's going to tell you that the variable isn't available. It's not in the model. It's in the model. It's just not in the model at the desired resolution. Yeah.
Yeah. And we did that because the data that we are pulling from USGS is coming. No, we are actually downloading it at the daily totals. And so when we did the ELM simulations last time, we added runoff to the list of daily outputs. So it gets written in the H1 file. If you only have monthly output, then we need to kind of do the aggregation on the USGS discharge side to go from daily to monthly. So there's a little bit of more code that needs to be written, but it's actually not difficult. It's we do this in ILAM all the time. So just to kind of make a note of that. Yeah, those are depending on the temporal resolution, the data is available and the model is available. We can make any of those situations work.
You can certainly make it work, but you want to be careful about it because then if you compare to other models that do have daily output, you're not really comparing apples to apples. And so I would probably be more inclined to add an option. Maybe you would have that entry in the configure file. You could have the entry twice, and once would be for daily and once would be for monthly. You just want to be cautious about that. So this is taking longer than usual. I'm not sure exactly what's going on there. I'm just going to open the cached result in the tab. If you're missing a step or I'm getting ahead of you, it could be that a bunch of people are hitting USGS servers all at once. I'm just going to show you here. This is a result available on ilamb.org/Nate step 2. This should be exactly what you're getting. Now you'll notice there's two things available. And when you click on USGS, what you get out of that is still a table. You'll notice the NSE and KGE metrics. Over in data information, I write down a representation of what they are if you're not familiar with those. The NSE is kind of the root mean square normalized by the variance of the reference. And the Klein-Gupta is like a harmonic mean of a correlation, the ratio of standard deviations, and the ratio of means. So it kind of compares three aspects of that model performance. oops, where'd it go? But what you'll see, what this confrontation gives you is, first of all, it gives you kind of a site plot, because the number 124888500, while it means more to me today than it meant maybe a while ago, it's not very helpful. And so we found that this would be much more helpful for people to be, first of all, oriented to where in the world is this watershed. And then then here it shows you, with the dot, and also what the contributing area was. And so this contributing area is coming out of USGS. And really, when we conduct watersheds, if you want to compare discharge directly, I think it's appropriate to compute over this shaded area. The odd thing is sometimes, and Jitu will talk a little bit about this, is sometimes the contributing area does not align to watershed boundaries. In this case, it does. You'll see kind of in dotted lines here, neighborhood watersheds, just to help give you an idea of what the delineation is. And sometimes the contributing area doesn't snap to one of those watersheds, which kind of confuses things. But we'll have more to say about that in a moment.
Yeah, and those dotted areas are HUC 12s.
Yeah, that's right. Yeah, HUC 12 boundaries. And so here you can see what the discharge looks like, E3SM versus USGS, which honestly, it came out a lot better than I thought it would, although stay tuned. We also kind of show just what the two discharges look like, and you would hope it to be very nicely correlated, but this is just something we came up with to help you see maybe where, if you're biased one way or the other, where is it? In this case, it seems pretty spread there. Oh, wow, it's still going. Okay, I'm going to break this for right now, because we're about to add some more models to it, and it's going to query it again. I'm not sure. It shouldn't need that much time, but it could be that the servers are just clogged down. It's another reason perhaps to implement some kind of caching. Is there any question about at least up to that point?
I'll just add that for the runoff comparison, in the example, we've just only were showing KG and NSE metrics, but
Oh yeah,
it's very easy to just say, okay, list and RMSE, list difference in the peak amplitude and the timing of the peak and things like that. So there are a lot of standard metrics that ILAMB calculates, and when you set up your ILAMB configuration, you have option to decide which metrics you want to be able to include. We of course pared it all down to just a few for the purpose of this tutorial. But
in this case, we're just providing kind of baseline, mostly because we would rather the community help guide where that should go, what makes sense to compare. And I know that's the subject of a lot of work already. Well, then we wanted to show one other thing, because it's not fun to do a benchmarking comparison and not have other models to run. And so we G2 did some legwork with some contributions that from others and we got some output from ATS, of which we have representatives online, and also from the Soil and Water Assessment Tool, SWAT, as well as the National Water Model. Now, these models, they are routed models. They have their own grids and things, and we don't have that output to show yet. Otherwise, we could show versus GPP if they implement a carbon cycle. But what we're showing you here is the output has been provided to us as just the discharge at the outlet, or the discharge and several other variables at the outlet only. So it's really more like a point model. And so this is just a demonstration that ILAMB can be very flexible about the kind of model that you want to define. And so let's integrate these models into our analysis. So I'm going to go back into my models directory, and I'm going to go grab this wget line here off of ilamb.org. This is just some point models that I cached And you'll notice as it expanded, it's just a CSV file for the national water model, one for ATS here, and then one out of SWAT as well. They're just CSV files. Okay, and so those are now part of our model archive, but we need to let ILAM know about them. And so in order to do that, we're going to insert some lines into our YAML file, and I'll explain one of them, and really they're all the same with just some slight differences. So let's just look at the ATS version. So again, just like with ELM, we make a block for ATS. You can give it a name. You can call this anything. In fact, if you don't include this at all, it's just going to call it whatever this block is. But you can call it anything, which might be helpful, like if you're running a calibrated versus uncalibrated model or whatever. You may have different options on. And this time, the model type is a point result. And this model type is intended to just read these CSV files in and then return them. So when you ask me for a variable, you ask me for the variable and you give me the site name, and then ILAM will query the model database and figure out if that variable is available for you and then return it back to you in memory. Just like before, we give it a color, we tell it the path of where those are found. We also need to give a mapping of the site to the file name. Now, ideally, this is something that we would talk with the good folks at ATS and have them embed somehow in the CSV file. I would rather read this number out of here, which at some point, when people ran these models, they needed to know the station ID because they needed to get data off of USGS to set up the run. And so, so we think that in the future, it would be nice for all of these models, to work with them and try to embed these numbers inside these CSV files, and then this wouldn't be necessary. I could infer which site everything was from. But as it stands, for every CSV file I put in there, I need to tell it which site it corresponds to. And then we set up a synonym. In this case, the synonym was watershed boundary discharge, and I think in the case of ATS, there's a difference between the boundary discharge and the total discharge. But I think in this particular file's case, this was the only version of discharge that was in there. But there's a lot of details, of course, for any model that would need to get ironed out to make this kind of a true comparison. And that's true of every model, right? And so if you just glance here, the same thing for these other models, it's really no different. The names were changed to protect the innocents. In this case, it's discharge, capital D discharge, and the file name is something different. And in this case, it's flow instead of discharge. There's no standard, right? And so being able to define synonyms is super useful in our benchmarking framework. So it's as simple as just adding these extra blocks now to our models file. And now whenever we rerun our ILAM run command, it's going to pick up these new models. Now, when it picks up these new models, it's going to try to run the GPP confrontation against them, right? And it's just going to return to you this variable not in model. I mean, just because it's in red doesn't mean it's a failure. In this case, that should be what happened, right? Because those point models don't have GPP in them, or at least not in the same way. They might return. I know ATS returns like a mean ET over the basin or something. So we could adapt that confrontation to work on that aggregated data. But in this case, these point models, they shouldn't be compared to this MODIS gridded data. Yeah, and so this time, fortunately, the final bit finished fairly quickly. And so we can again navigate into our build directory and say Python m http.server. Right, and let's close now the stuff of ilam.org and reopen this. And now you'll notice that our comparison is getting slightly more interesting. We now have ATS, we have other models, if we click on now this, you'll see here that you get relative coloring. Now you also see that the ELM just instantaneously river routed to the site. Discharge wasn't such a great comparison, which isn't a surprise. Take a sigh of relief, all you watershed modelers. The result confirms the existence of all of your models. It should, right? It should be much better to actually route the model. There's going to be time dynamics in there that are not captured if you just instantaneously do that. And you can see then how all these models kind of compare to each other. And whenever you click on a particular one and click down, all the plots change. Or you can just click here to the all models tab, and it will show you the comparisons all in kind of one. Or you can go to the scatter plots. Again, using the zoom, the browser zoom is your friend. And you can kind of see the merits of what ATS gets. Well, they seem to be, now that I'm thinking about it live, I'm not going to get it right, but like they're a little higher there whenever the USGS is low for low discharge rates, right? So the low flow, it's a little too high. But you see like SWAT over here, right, under predicts some of these extreme events too. This helps you kind of understand the character of what's going on. And so I think hopefully this demonstrates at least what we see could be the value in setting up this kind of system. And what I hope it also shows is kind of like it's ripe for development. We need people to chase down observational data sets, which that could be through peers, but also just through talking with others. We would need to identify like which watersheds are the ones we really want to run at. Where do we really need to know, or where do we think our resources would be limited? So you would want to pick carefully the watersheds that you run where you have a lot of information, a long time record perhaps, and then you actually have to have people to go and run them. But the framework is there, and I think we run have the possibility to really compare and understand differences in models. Is there any other question about the tutorial part? I can come back there, but.
And I'll just note here that the way ILAMB is set up, once you saw the you don't really have to have these configuration files specific to a single watershed. You can, if you have the watershed simulations over a lot of different watersheds, they can all be pulled together in one configuration file, and these final output pages that are generated will show everything in one place. We've talked about, there are some integration metrics that one can start to build on, but that's really a conversation that they'll have to have with folks that are running these watershed scale simulations to find out what's going to be useful feature to add.
And I think if it were to be something that the community decides they want to work together and push forward on, you need to be very explicit about what gets set up and run. I think you have some examples about that to show as well. Yeah. But it's tricky to know whether or not you're getting a contributing area, which might be many watersheds, or you're getting the HUC 10, which is different than the HUC 12s, and make sure you're comparing apples to apples is actually quite challenging.
Yeah, the folks that are running these models and analyzing these models, of course, have better insight into kind of analysis that's appropriate. And I have a few thoughts on, based on some of the work that Nate and I have done, to just show in a couple of these slides. But really, what we want is to get input from everyone, so we can just start to add better metrics, better capabilities, better way of aggregating these results. So so the ILAMB, can be useful for everyone who's running watershed scale simulations with any of these models. Any feature that's not there, I mean, would love to just get your input and start to add them. So I'll just quickly go through just a few slides I had. So we've implemented a few metrics, right? But there's a lot more that we can start to think about that should be included, right? We talked about some high flows, low flows, but it's not really a huge amount that we have there. But are there seasonal biases and so on that we want to be able to capture and make it as a standard part of these evaluations? So that's really kind of where we need some feedback. Again, are there equal hydrological functional metrics, just like you saw for same type models that we can start to build? Most of these models have not just flow, but also ET being simulated. Are those relationships that we want to be able to examine and include as a part of this? This was mentioned that right now we're just using these point observations that are being saved, but we would very much like to go back to original model outputs and actual gridded outputs, and being able to, like, even for ATS, it's a non-structured grid, unstructured grid, but write custom readers so we can directly read those files within ILAMB for not just simply a point, but rather full gridded data set, and be able to use it in evaluations. And then this topic of sort of quantifying uncertainties. There's a lot of mismatches between model and observations, and for the particular type or particular data set that we used for this tutorial, I want to just show you a few mismatches that are this obvious that we really want to be able to address, and see if there is a way to be able to capture these and include it. So when we are looking at these metrics, we put it in the right perspective, so we know where the mismatches are and how to actually interpret these results. So I have a couple of slides on that, and this last thing, if we have lots of model observations. So we have we didn't use it today, but Samindra, who's on the call today, was able to share with me ATS output for 6 or 7 different watersheds, and we put it all together in a single evaluation. But if we had a lot of those watersheds across the country, are there regional scale evaluations? So not really just looking at a single watershed, but rather combining the model performance across regional scale, across national scale, will that be useful, and what would those evaluation metrics be? And that's the discussion that we can have. And if we know what metrics will be useful, I'm sure we can figure out a way to be able to include those within ILAMB. So this idea of mismatch. So there's a difference between the watershed that the models were simulating and the contributing area that observations, those gauge stations have. And it's really kind of important to see those differences. And I just have some plots. Right, so I took those 2 different basins that we have, right? And if I just simply look at the topography, and if you plot a density plot, right? So this is try to look at the distribution of the basin that's the model is simulating. This is the simple elevation data. And then for the smaller basin that we saw in some of my earlier slides about that the observation is saying, they have very, very different characteristics. And I just simply took these distributions and then ran these standard statistical tests to determine, are they being sampled from the same distribution? And these 2 tests that I just have listed here, they show that they actually are statistically different distributions. So is the comparison appropriate when it's not appropriate? I don't know the answer, yes or no, but something that we can start to think about and talk about. And I did the same thing, and I went back to Damit precipitation, and Damit precipitation was what's being used to force most of these watershed scale models, and even actually ELM models. They are all being forced using Damit. And I just simply did the same thing. To look at the distribution of precipitation within this larger Huck 10 versus this combination of 2 Huck 12 that's observations are aggregating or saying. And again, the same story. These distribution functions are very, very different. So in some ways, the routed models are actually doing a better job, because routed models do know those those topography, and they are actually probably aggregating. And I was not able to get, bring in the contributing area that, at least ATS type models are saving to be able to bring in this comparison. But we can start to think about how do we bring those in. So these evaluations are put in the right perspective. We know what the difference is between what the model's contributing area versus the gauge stations contributing areas are. And then this is just my last slide. Now, again, send us your feedbacks. There is a ILAMB web. I know that Nate is very good about looking at PRs and accepting those PRs. So if you have suggestions, send us an email, find us in the hallway or at the PI meeting or whenever, and then share your model results, because having a sample model results to work with really enables us to be able to try different things, implement these metrics and make sure that it actually works and it looks useful. I mean, Saumendra's 6 model files that he shared with me really kind of help us a lot on what we were able to do by having a set of data to work with. So yeah, and then we'll of course, Nate already touched upon this, that we'd love to work with the model developers to figure out changes that we can do within ILAMB, and then what are the changes we can get done in the output files themselves, so that they are self-contained, so we don't really have to hard code things within configuration files and so on and so forth. So I'll stop there. Hopefully, we can have some discussions. We still got 25 minutes, so some time. Of course, we can go back to any of the steps that Nate went through. Any other questions, comments that you have? Were you guys able to follow up through the steps and get the outputs working in your own Conda environments? Of course, we try to document all the steps so you can reproduce it later on and still have all the information that we talked through today.
And in particular, is anybody stuck on any of the steps? Because it's a good time to ask these guys who we've got captive here to help resolve some of these issues.
This is the problem of doing things on Zoom, right? You cannot see anyone.
The other thing that I would say is that we've been just sticking assets into that ILAMB Watersheds repository. If you look at the link to the tutorial information, feel free to raise issues there or discussion, or we're just trying to leave that as a place where we can record what we've got and kind of use it as a discussion place to perhaps push forward. And so that's an appropriate place if you have some comment.
Yeah, maybe we'll do, I think we should do like follow-up surveys from both of these hackathons, because we would also like your input on the other kinds of things that you think would be helpful. If you have suggestions for other kinds of tools, or
you have a tool,
or you have something you would like to give a hackathon on, we want to find that out too.
But love to see one on some of these watershed models.
Mm-hmm.
Maybe you guys have already done that, Ethan. I don't know.
Yeah.
I don't know if the awkward silence is good or not.
Yeah.
It feels not good, but I don't know.
Yeah.
You did a great job.
I hope somebody was able to go all the way through. Was anybody able to go all the way through?
I went all of the way through and I am not the best at these things. So that says something about your documentation.
Yeah, we call that a success then.
That's awesome.
That's good because yesterday evening it was breaking catastrophically.
All right.
The other thing that I will just add here is that again there are a few more codes that I'll summarize all and then send it put it in a GitHub repository and then add the link in the Slack channel we have. But when we were working through these watershed scale simulations and working with watershed scale evaluations, one thing we realized is that ILAMB, for example, provides half a degree resolution data set for global scale simulations. A lot of them. You saw that a long list on Forrest's slides, but for watershed scales, the ELM simulations that we did 2 weeks ago were done at a kilometer resolution. These watershed scale simulations with ATS, I'm sure they are running at meter or sub-meter resolutions. So that in order to do a fair evaluation, we also need a high resolution data set. And there's just no way we can actually take global data set at 500 meter resolution from MODIS and make it available. So by pulling it directly from USGS websites makes it easy for these watershed discharge data from USGS. We don't know which site, which gauge station you may be working in. So using these REST APIs that USGS provides makes it super easy. So we try to think through, bring in at least data set, use it in this particular tutorial. So you have to start with minimal amount of observational data and make the step from going to your model to evaluation with ILAMB as seamless as possible. So there are a lot of DOE data sets that are available within various different data center or others. I think all those data sets, if there is a more systematic, a programmatic way of accessing those data sets, that makes the integration within ILAMB a lot easier. So we don't really have to, we don't really have to curate and share those data sets ourselves. And if you know of other data sets that will be good to include, send us a note.
Somebody had asked about implementing the data types. It's a bit advanced, I guess, advanced user. But I just kind of wanted to show that there's not a whole lot to it. There's a bunch of imports and things that I'm using here, and I have an extra function to compute the cell measures because the areas actually, if you go into your raw output for E3SM, there was a mistake made and the cell areas are actually 4 orders of magnitude too large, which is so I have this thing and that will, when you give me the X-ray data set, will just populate over them. But the real object is here. It uses a data class. You don't need to use a data class. I just did use a data class. And internally, you can make the internal representation of your model whatever that you want. In my case, I have a name, a color. Some data entries will be required, like name and color, because they're used by other parts in the code. But the rest of this, synonyms, files, variables, all of these things, these are things that I use internally to get you the right information. And so I have, in the new way of thinking about things, I have a function called find files, which dictates how to go in and look for which files are where. You can see here that it's following the H01 pattern, and it's looking for files that end in netcdf, and follow this particular pattern. And it builds, you don't have to actually step through all this code. In this case, it's just looking through and building a pandas data frame, which allows me to query. So whenever a user asks for a particular variable at a particular frequency, I can tell you if it's there, what's the time bounds around which it exists. So that way, if you ask for a smaller subset, I don't load all of the data files and then subset it. We only load the data files that will contain the time frame that you want. So it's a lot faster. And then I implement this function get variable, which again allows you to specify synonyms. You can give me synonyms directly, or it also reads from the internal ones of the particular model. And this is the little bit of magic here that regrids the data using the using a pandas data series. Is it a pandas data series? I always get this other way around. Yeah, creating a pandas data series, you set the indices to time, lat, and lon, and then tell it to Xarray, and it builds a gridded data object for you. So anyway, this is all that happens internally. Essentially, if you want to implement your own model type, you just need to populate get variable, right? And essentially, given this kind of information, return to me the variable in memory. And this returns a data set, which is kind of like the Xarray data set, which is the new way. And then essentially, this is the old way where I call that function and then load my own object instead. And then there's just a little bit of stuff to add a synonym, which you could just copy and whatnot. And so there's really not, I guess it depends on your tolerance of ugly code, but there's not that much to it, right? Because all I'm doing is I'm organizing information and providing a routine to load something into memory. I don't know if that was helpful for that, but I didn't recognize your voice, whoever asked that question. But oh, and it looks like Dan has a comparison with 2 versions of ELM.
And SP mode wins.
Yeah, so this is what I think, if you're looking at the SP results, I guess I can share my screen again and make a comment. This is what I think is happening here. I think that this bounding box is actually over just those 2 HUC12s, right, which is actually a smaller subset of this bigger region. And so instead of trimming away the reference, which is what I thought happened, but it's not trimming away the reference, it's actually interpolating to the closest value. So I think the ELM result is this tiny bit in here. And you see these vertical bands, you can see them pretty pronounced here. These are nearest neighbor interpolants back to the closest cell in the ELM output. And this isn't what I thought it was doing. I thought it should actually trim away this, and so you would get just the square over that output. But all of this can be avoided by being more careful. We could change this to be just those 2 HUC12s that we showed in the contributing area. And then also, you know, we could run the model over just those cells too, right? It would be faster, slightly faster, and that would clean up the comparison. Cool, Dan. Thanks for sharing.
Yeah, no surprise, SP version did better because it's driven by the Modus LAI.
Oh,
If you actually compare the 2 GPP results, you can see much more detail in the SP version, because like the BGC version seems like it has pretty uniform LAI, and it's when it's predicting LAI, but then there's some grid cells where it's 0. So it's either 0 or something like almost constant. So it kind of gets where the tree line is, but yeah, it doesn't really have the detail in LAI that you see.
Oh, so is that why we were seeing some 0 GPP cells? It's 0 LAI.
Yeah, if you look at the version where you can look at both on the same page, you can kind of see how those line up.
Yeah. Yeah. Yeah, they're light. They're definitely light in SP mode. But they're 0 in BGC.
Mm.
Interesting. Yeah, we find that we learn a lot about models when we do these types of comparisons. Sometimes it's not like science stuff, but still valuable. You realize assumptions and things that maybe you weren't aware were part of your calculation. If you just kind of sum it all up and look at a curve, all that is lost, right?
Right, Forrest, goes out.
Yeah. Any other questions or comments from folks? If not, thanks very much for coming.
Thanks, everyone.
Thanks, G2 and Nate.
Yeah.
For all your hard work on this. And we'll be doing more of these in the future. And we hope to see a lot of you at the cyber infrastructure meeting or at the ESSPI meeting next month in Bethesda. Thanks, everyone.
Thanks.
Thank you.